So, how exactly do you teach a machine to make a good decision, especially when the world doesn't always play by the rules? Well, today we're going to break down this really powerful framework that helps AI do just that, navigate uncertainty and, choose the best path forward. All right, so meet our little agent for this explainer. Its goal looks simple enough, right? Just get that shiny diamond. But there's a pretty serious hazard right there in the way. And as you're about to see, just trying to walk a straight line? Yeah, it's not quite as easy as it looks. And that really is the central question here, isn't it? When the outcome of what you do isn't a sure thing, how do you program a strategy that gives our robot the best possible chance of success in the long run? Well, that is exactly what Markov decision processes are all about. Okay, so to really get our heads around how this all works, we're going to use a super classic example from AI research. It might look like just a simple game, but trust me, it perfectly captures this whole challenge of making decisions when you're not sure what's going to happen next. The rules here are pretty straightforward. Our robot kicks things off in the bottom left. See that blue diamond? That's the goal. It gives a nice positive reward of +1. And the fiery pit? Yeah, you want to avoid that. It's a terminal state that gives a negative reward of -1. Oh, and that gray square in the middle? That's just a wall. Our robot can't go through it. Okay, but now, here's the catch. This is where it gets really interesting. This is not a normal game. The world is non-deterministic, which is really just a fancy way of saying that the robot's actions, well, they don't always go according to plan. So let's say our robot decides to go north. You'd think it would just go north, right? Nope. There's only an 80% chance it actually moves north. Then there's a 10% chance it kind of veers off to the west, and another 10% chance it slips over to the east. Every single move has this element of pure chance baked into it. And this just perfectly illustrates the problem we're dealing with. The robot gives one single command, like go up, but the world can spit back 3 totally different results. So you can see you can't just plan a simple path like up, up, right, right anymore. You need a strategy, a real strategy, that works even when the world is this unpredictable. So, to solve this puzzle, first we need to learn how to speak its language, and that language is the language of Markov Decision Processes, or MDPs for short. It's what gives us a really precise way to define our robot's world and all its rules. First up, we have states. A state is really, it's just a specific situation the agent can be in. You can think of it like a snapshot of the world at one single moment. And in our grid world, this is super easy to see. Each and every square the robot can land on is its own unique state. The state just describes where the robot is, and that's really all we need to know to figure out the next best move. But states are just one piece of this puzzle. Any MDP is defined by these 4 core components. So you've got S, that's the set of states, all the squares on our grid. Then you have A, the set of actions, like moving north, south, east, or west. T stands for the transition function. That's the slippery controls, the whole 80-10-10 probability of where you'll end up. And finally, there's R, the reward function, which is what gives us the +1 for the diamond and the -1 for the fire pit. Put them all together, and these 4 things define the entire game. All right, so we've defined the world, we've laid out all the rules. Now for the really big question. How do we find the absolute best way to navigate it? We need to build a strategy. So in the world of MDPs, that strategy is called a policy. You'll often see it represented by the Greek letter pi. A policy is basically a complete instruction manual for every single possible state. So for every square on our grid, the policy tells the robot exactly what to do. Go north, south, east, or west. No exceptions. But think about it. There are tons of possible policies, maybe millions. So how do we find the best one? How do we even measure if a policy is good or bad? Obviously, a policy that just tells the robot to run into the wall over and over isn't very good. But a policy that gets you close to the diamond but also risks falling into the fire pit, that might be even worse. The answer, the key, lies in figuring out the value of each state. And the value isn't just the immediate reward you get for being on a square. No, it's the total reward you can expect to get over the long haul if you start from that square and then play perfectly from that point on. I really like this comparison because it clearly separates these 2 big ideas. On one hand, you have the values. That's what the AI thinks. It's like a map that shows the long-term desirability of every single square. On the other hand, you have the policy. That's what the AI does. It's a map of the single best action to take on each square. And here's the crucial part. If you have the value map, the thinks part, figuring out the policy, the does part, becomes super easy. You just always move to the neighbor with the highest value. Simple as that. Okay, but there's a really subtle but absolutely critical detail in how we calculate that long-term value. Because as it turns out, not all rewards are created equal, especially when it comes to timing. Just think about it in human terms for a second. Would you rather have, say, $100 today or $100 a year from now? Yeah, most of us are going to take the money today, right? A reward in the future is just less certain, it's less valuable than one you have in your hand right now. And it turns out we often program our AI agents with that exact same preference for sooner is better. The way we do this is with something called a discount factor, usually called gamma. It's just a number between 0 and 1. And for each step we look into the future, we multiply the potential reward by this gamma value. So for example, if gamma is 0.9, a reward that's 2 steps away is only worth 0.9 times 0.9, or 0.81 of its original value. This little trick does two things. It makes the agent's behavior way more realistic, and it also, for technical reasons, really helps the learning algorithms figure out a solution. Okay, so we know we need this value map to create the best policy, but how does the robot actually build it, from scratch? How does it figure out the true value of every single one of these squares? Well, it uses this really elegant process called value iteration. And here's the aha moment. Instead of trying to solve the whole giant puzzle at once, it just uses these simple local updates over and over and over again. First, you start with a blank map. Just assume every square has a value of 0. Then, for each square, you calculate a new updated value based only on the values of its neighbors. You update the whole map, and then you just repeat. And with every single pass, the estimates get a little bit better, a little more accurate. And what happens next is actually pretty fascinating to watch. Through this simple repeated process, the positive value from the diamond and the negative value from the fire pit, they start to kind of bleed out or propagate across the entire grid. It's like a ripple effect. The squares right next to the diamond become valuable. Then the squares next to them become a little valuable, and so on. It's amazing, really. This huge, complex, global problem of finding the best path from anywhere on the board gets solved by just repeatedly looking at your immediate neighbors. You do that enough times, and a perfect value map just emerges. So once that value map finally stabilizes, when the numbers pretty much stop changing, all the hard work is done. Finding the optimal policy becomes almost trivially easy. From any square on the board, the best action is always, simply, to move towards the neighboring square that has the highest long-term value, the highest expected utility. And just like that, our robot has its complete, perfect instruction manual. So starting with just a simple grid, we've basically built a system for making optimal decisions in a really complex and uncertain world. And this idea? It's the foundation for everything from self-driving cars and robotics to high-frequency financial trading. Which really leaves us with one final thought. Now that we have this incredibly powerful tool, maybe the biggest questions are no longer about how we make machines decide, but about what decisions we're going to ask them to make for us.